All right, so we'll get going. So I actually didn't officially introduce myself this morning when we started. So I'm John Teagues, Vice President here. Been with WaterTech for about 12 years. Before WaterTech, I was with a water and wastewater equipment company. And then before that, straight out of college, was in operations for lots of biological wastewater systems. Worked for a company who built wastewater treatment facilities for dairies, food and beverage plants, things like that. So kind of where I cut my teeth. Right out of business school. It makes a lot of sense if you don't think about it. So we're just going to talk through a few different things, different types of wastewater that you treat biologically, what types of wastewater you can, and what characteristics of wastewater can't be handled by biology. Chris alluded to some of these things too, but different types of biological systems. Main two differences is with air, without air. So aerobic systems require air, anaerobic systems do not. And so we'll take a look at those two different types of systems and have a kind of a conversation and view about some of the bigger costs related to biological treatment. Everything okay with sound?
Yeah, sound great.
Cool. So as we look at wastewater constituents, what's in wastewater? What can be treated biologically is mostly organic material. Fats, oils, and greases can be, but too much FOG is going to be toxic to the biology of a wastewater system. Nutrients as well. Chris said we haven't talked a lot about phosphorus removal, but that's been, when I got into the wastewater business 20 years ago, phosphorus, they went down to a 1 milligram per liter limit. Now we're down at 0.075. So phosphorus removal is really, really critical. Nitrogen and ammonia removal has been around for a long, long time. So those are the types of waste streams that biological systems can handle. What don't they do? They don't treat for pH, right? So if you send a caustic load of stuff down to your waste biological treatment plant, it's not going to neutralize it. There needs to be some means of doing that. The reason that a lot of you here or metal castings companies and foundries that they have to remove metals from their wastewater before they send it to the municipality is because biological systems cannot remove high levels of metal. That's why those pretreatment facilities are so important. Inorganic solids, so lots of different things, but grit and just different things that are inorganic are just going to pass through a biological system. How many people knew that temperature was a pollutant? That's more and more now these days. Dairies, when they discharge water, it can't be too warm because the high temperature water can affect the biology in the receiving stream where they discharge. So, I mean, the temperature will kind of go down in a biological system, but we're not controlling it. Chloride, one of the reasons you hear a lot about municipalities trying to limit the amount of chloride coming in, so through salt, regenerating water softeners and things like that, is because biological systems do not remove chloride. So a dairy might have a cheese plant, really high chlorides. There's nothing that the biological system is going to do to remove those chlorides that come in. And then we'll talk a little bit about toxicity as well. So toxicity, there's chemistries that are used in industrial processes to, especially food plants. You need to kill things in your piping, the manufacturing facility, so that you don't have any toxic or bacteria in your food product. Well, those things carry through into a biological system. If they're still present, they're going to affect your biological system. If they make it into the effluent of your facility, you'll have toxicity issues in your receiving water. So a little talk about organic waste. Won't read through all of these here, but kind of what is organic? It's derived from plants and animals. It can float. It can also be dissolved. Measured by COD, BOD, basically oxygen demand, either chemical oxygen demand or biological oxygen demand. Just two different readings that kind of measure the organic strength of the wastewater that a wastewater treatment plant has to treat. And they require oxygen to be treated. So when you're looking at a biological system, I think if we go back to my first slide, this is a bunch of wastewater with a bunch of bacteria that generally has kind of that brown color. So that bacteria, in order to consume the organics that are there, it needs oxygen, just like you and I need oxygen to breathe and to survive. And so that's really kind of what you're looking at here. Is it's not crap. That's just wastewater and bacteria mixing together. Interesting sometimes to get a sense of how strong different types of wastewater are. This is all focused really on dairy. We're in Wisconsin. There's been a lot of studies on the strength of certain dairy products in terms of their COD concentrations. So kind of generally the combined wastewater coming down to a wastewater plant in a dairy will be 2,000 to 5,000 milligrams per liter. But that's why you were talking about sometimes you'll get the cheesy waste. When you start getting spills of whole milk or cream, even whey, these numbers start to really spike up, and biological systems will start to really struggle with loads this high. That's why one of the things we'll talk about that dairies will try to do, or even industrial processes, is segment those high strength waste streams so they can be handled separately or bled in over a period of time so that you don't overwhelm your biology. So play a little game. First one, and what did we think? Is cotton, based on what we talked about, is cotton going to be organic or inorganic? I spent a lot of time on this animation, so I want lots of oohs and ahs. So yes, it's organic. A car tire. Oh, look at that. Somebody didn't proofread my slides, including myself. The sole of my shoe. Inorganic. Let's see what other spelling mistakes we have. Ash. Yep. I tried not to do these in order so it wasn't obvious too. Chewing gum. Inorganic. I was playing around with some kind of fun things. I threw Donald Trump's hair in here because hair was one of the things. Is it organic or inorganic? But I don't think anybody knows what his hair is. But so back in the 80s, inorganic. I didn't want to get too political though, so not the way we are. Chicken bones. Yep. Wood chips. Organic. Lots of these at my house. Depends on what?
Where they're coming from.
And then obviously we have one slot left, so our glass bottles. So these are the types of things that, as if they're small enough, again, if you take a big chicken bone, throw it into a wastewater plant, it's not going to get consumed. But if it's in a small enough particle, then it can handle those things. So just what we call different unit processes. What makes up a biological wastewater treatment facility? Primary treatment, that's where we're trying to get rid of those big solids, fats, oils, and grease, pH adjustment sometimes, trying to get the water prepared for biological treatment. Equalization is huge in a biological system. It's huge in any wastewater system, really. But biological systems like steady state, nice consistent flow rates. That way you have nice even retention time within your treatment tanks. Your clarifier is not spiking up and down, or your DAF, whatever your solids liquid separation is. Usually a great place to do pH control as well. So then we have our aerobic or anaerobic treatment basin. That was the first slide with all the brown stuff. That's basically what that is. That's where the actual treatment is occurring. And then what do you have to do? You have to separate the liquid and the solid. So you have your clean water all mixed together with the mixed liquor or the suspended solids, the bacteria that's doing the work. And then you separate that in your solids liquid separation, then you return the solids back here. So it's a kind of a recycling process. And then if need be, you'll take the effluent from your solids liquid separation, filter it if necessary, and then go out to your effluent. And then, as we'll talk about, the outcome of biological treatment is the more waste you treat, actually the more bacteria it reproduces as you treat waste. So the more waste you treat, the more leftover you get, and you have to waste some of those solids from your biological system. Otherwise, you end up with a poor population of biology that will cause all sorts of other issues. So what we do have to do is take a certain portion of these return solids, waste them into a sludge tank for disposal. It'll go to landfills. It'll go sometimes on fields, farm fields as fertilizer. And then that step 2, dewatering. This is usually going to be liquid. If you can't handle that much liquid out on farm fields or whatever, then you can dewater it, basically reduce the amount of volume that you have. So this is a basic. When you get out into the field and you actually see what different places do, it gets a little bit more complicated. Oh, sorry, forgot about the fancy money slide. So areas of cost for each one. On the aerobic side, you're going to have a lot of energy requirements in your aeration basin. You have to blow a lot of air into that tank that I showed you at the beginning. It takes a lot of energy to do that. Oftentimes at a municipal plant, that's their largest cost, is just aerating all the different basins that they have. Solids liquid separation, depending on the technology, you'll have some chemical usage there. If you can do gravity separation, then that can be relatively low. Same thing goes for tertiary filtration. So if we are adding products to get phosphorus down to 0.075 milligrams per liter, you can potentially have some decent chemical costs there. Dewatering, as Chris talked about, with your sludge presses, your belt presses, screw presses, multi-disc filters, those are typically going to be large chemical users as well. And then if you have to get rid of it, if you're hauling to, especially if you're hauling to a landfill, you have the cost of hauling it and then the tipping fees for getting rid of it. If you're lucky enough to live in a rural location where farmers will actually take the waste onto their fields, the disposal costs won't be too bad. So here's where things start to get a little weird sometimes is different companies, and different customers decide, hey, I need to do different things and different ideas about how you do it. So this is actually a customer of ours where similar things, water comes into an EQ tank, but their return solids go back to the EQ tank. So they're actually doing some biological treatment in their EQ tank. Then they do some separation of kind of fats, oils, and grease and things from the DAF before they send it to their aerobic. And then they do their solids liquid separation and they send it out. They have a high strength diversion for those spills and things that come down. They can separate those and then bleed those back into the DAF and treat them if needed. And then their sludge tank for disposal. So in real world, depending on each particular customer and who they're working with, things will start to still some of the basic unit processes, but sometimes you see some pretty creative things done out in the field. This also is another customer of ours where they're running both aerobic and anaerobic. So they'll take their normal strength waste, they'll come in, do some biological phosphor removal in a selector tank, their aerobic treatment, SLS, and then sludge tank, so that we've seen already before. What they do though is they take their high strength waste, they still bring it down, but they send it right into anaerobic. So we'll talk about anaerobic a little bit more, but it can take higher organic loading when compared to aerobic treatment. So it also generates methane, one of the advantages of an anaerobic process. And so they actually take the methane off of their anaerobic treatment, run 2 generators, sell electricity back to the grid when they're working. So just again, variations on what real world applications look like. So just we'll go into depth a little bit more into each one of those unit processes. The goals of primary treatment, again, it's removing a lot of the things that the biology can't handle. So solids, some of that high strength waste, pH, fog, just trying to get it as prepared as possible for the biology to handle. So screening, large solids can clog downstream. I have no idea what that is, but I don't want to be the guy that has to clean that out. And you definitely don't want that getting down into your biological process. It'll hurt the biology, but it'll also clog up your pumps and lead to other maintenance issues. So you want to actually get a lot of that stuff moved out. This is a canning factory that I worked at down in southern Indiana. They were cooking inside cans. They were making soups and things and beans. And so they had these nice self-cleaning filters that just gets all the beans and chunks and things out because they just would cause havoc on the biological system. So these were nice. These would rotate. The beans would come over the side and then they just fall into a dumpster. Automatic cleaning is always, if you can do it, one of the best options because nobody wants to have to clean that off. Fog removal. So again, high levels of fats, oils, and grease. If you're there's a case study here. Actually, one of our customers a number of years ago, 15, 20 years ago, they actually worked with this company that put in these oil skimmers. But this is a chicken processing facility, lots of oil and grease that they don't want to have come down to their biological system. So using a rope skimmer, they've actually moved on to actually have a big primary clarifier now where they try to pull a lot of their oil and grease out. And why this was such a good option was they were able to sell that grease somewhere else. So again, sometimes you'll talk about waste now becoming not only a cost, but you can sell some of the byproducts of the waste. You know, selling grease or oil back to somebody else that can use it for biofuel. In the case of anaerobic, we have methane that's a usable byproduct that we can actually make some money on instead of just costing us money. Flow equalization, again, it's a big flow equalization tank, lots of places, especially food plants. CIP in the evenings, you get 80% of your flow and loading happen then. If you have a nice equalization tank, it can buffer that, run it through your plant the rest of the day. It equalizes the organic loading because most of your organic loading is coming at night, so you kind of dilute it down with the flow from the rest of the day. Nice spot for adjusting pH and just letting things kind of chill before they make it into the biological process. Here they're using air to mix it. Anytime you can use air is a good thing. It kind of keeps things fresh and not smelling too bad. pH adjustment, Chris talked about pH, pretty straightforward. Calibrate your pH probes and try to keep for biology in that 7 range. Obviously they can handle 6 to 9 just fine, but once you get too extreme, then you run into performance issues. So aerobic treatments typically called activated sludge. This is what the large majority of your municipal plants are doing on a larger scale. So it's an aerobic biological process, uses microorganisms, that's all the brown stuff that was in that tank, to reduce biodegradable organic pollutants from wastewater. That's it. Remove COD, BOD, and these are some of the different major components of the treatment tank itself. This is all the science stuff that I'm not necessarily an expert in. The important thing to understand is that we're taking organic waste, we're adding oxygen, exposing it to microorganisms, there's nutrient, and then some inert stuff. And it's converting it into carbon dioxide, clean water, and you're creating new microorganisms. So this idea of creating new microorganisms is referred to as a yield rate. So every pound of COD or BOD that you bring into a facility, you're going to generate so many pounds of new organisms that you're going to have to deal with. So see, it gets bigger. Activated sludge, been around for a really long time. Talked about it being the most commonly used method to treat water that's going to go to a surface water discharge, because you can get very high quality effluent, very clean water. And then you do have some ability to remove nutrients. You can get rid of ammonia. You can, it's a little bit more finicky process, but you can design an aerobic system to enhance biological phosphorus removal. Typically, to get really low with phosphorus, you have to use chemistry, but you can design your biological system to remove phosphorus as well. Limitations, high energy usage. You need all that air. Blowing air into a 25-foot deep tank takes compression and a decent amount of volume as well. So it takes a lot of energy. It will be susceptible to upsets. We'll talk about some of the parameters that can lead to that a little bit later on. Moderate loading rate, so how much COD you can treat per volume in your tank are moderate compared to something like an anaerobic digester. And relatively high yield rate, so that was that yield rate, how much sludge does it produce for every pound of COD is relatively high in an activated sludge process. So this is just an example. This is the same canning factory down in southern Indiana. It was a pretty large facility, about 1.2 million gallons per day. You have recirculation pumps in your tank, so that's just mixing. And then these are blowers that blow air kind of into the discharge side of this. This recirculation pump goes into the bottom, diffuses that air, because you want a complete mix in your tank, and you want relatively fine bubble, because the more small bubbles you have, greater the surface area, the better your oxygen transfer. So a lot of times, or we should have dissolved oxygen sensors so we can control dissolved oxygen, helps make us more efficient with the amount of energy that we're using. And then always, one of the things that's a big problem in wastewater plants, if they're not in control, is foam. So these are actually little spray nozzles that if foam starts to develop, one way to control foam is to just spray on top of it and knock it down. So having some ability to control foam is pretty important. Some of the parameters we looked at, just talked about dissolved oxygen, basically amount of air that's available for those bacteria to respirate and treat the waste that they're exposed to. Too much waste energy can promote growth of detrimental organisms like filamentous and other bacteria, but filamentous can also be caused by not enough oxygen. So there's pluses and minuses. If you go too long with not enough air, you start to go septic, and that means your whole system stinks. Which I worked at, they're not in business anymore, but Golden Guernsey Dairy, they had a wastewater plant out in Waukesha. It was the first time I was in wastewater, and right across from the county fairgrounds. And we had a system just went septic on us right across the street during the fair, and just all sorts of complaints about odors blowing over onto the fairgoers. Another way of measuring that the amount of air is ORP. So sometimes that's used with or in addition to dissolved oxygen to kind of measure the amount of air available in your system. Mixed liquor, suspended solid. So mixed liquor, the term is that's the brown stuff in your mixed tank, all the stuff mixed together. The MLSS is basically how much bacteria is in that tank. So we want to control it, different ways of doing it, but somewhere usually between 3,000 and 6,000 milligrams per liter, depending on a lot of different factors. Again, it's one of those parameters that a particular facility has to manage, because too high, too low can cause issues. And how you control this is through that wasting of the sludge. You run a TSS, hopefully on a daily basis, and you can adjust how much you're wasting from the system to kind of maintain that. MCRT, sometimes called sludge age, is basically how old the sludge is, that bacteria within your system. So typical range, 5 to 15 days. If you have, again, sludge is too old, you have problems. Sludge is too young, you have problems as well. And when I say sludge, it really means this mixed liquor, how much bacteria you have in your system, how old it is, those sorts of things. Hydraulic retention time, how much time a given gallon of water spends in your system. It's really nice to have 24 hours of retention time. We have a customer, one of the ones that I had up here, they're about 12. So the longer you have, the more consistent you can be, but the longer your bacteria has to treat the water, it's good. If it's too short, then it's really hard to completely treat everything. And then this idea of food to microorganism ratio, F to M, basically the ratio of that, how much COD, BOD you have coming down to how much bacteria you have. So again, it's one of those parameters that you have to keep in balance to keep a healthy system. So here, when activated sludge goes bad, lots of things can happen. I talked about foam, odors, this system here. The healthy system should look like the one at the beginning, where it's a light brown color, kind of have an earthy smell. I don't know what it tastes like. But you can end up with foam, you can end up with black sludge, all these different things. So two areas that we hear a lot about causing issues now. One is sanitizers. So when I talked about toxicity earlier, there's a lot of different sanitizers that especially food plants will use to treat all their process piping and things like that. And again, those are designed to be very aggressive at killing biological matter, as they should be. Two of the biggest ones that we see now are peracetic acid and then quaternary ammonia compounds. So those will, if used too much, those will flow through the system, end up in your biological wastewater treatment plant, and they will cause problems.
Which one's worse?
They're both. I've seen more issues with quaternary ammonias. Peracetic acid, you can actually use SBS, sodium bisulfite, to neutralize it. So it's, from what I've seen, it's a little bit easier to control. It'll still give you issues, but there's a lot of different quaternary ammonia compounds. There are products that neutralize it, but I've seen a lot more problems with quats than I have with peracetic acid. And then again, if those carry through into your effluent, then permits have limits for phosphorus and BOD and temperature and all that, but then facilities have to run toxicity tests, wet tests on a regular basis. And these types of compounds, if they're present, will cause you to fail a toxicity test.
We just had a customer municipality, one of their customers, which was a cheese plant, dumped half a 55-gallon drum of PAA down the drain, and I think it's been 3 weeks and it's still not back to where it should be.
Wow.
So
these are very, yes, these are very aggressive biocides, very good at what they do. That's why they give wastewater plants lots and lots of issues. And it's always the case that a production plant isn't always totally upfront and honest about what got sent down the drain. It's a universal problem. He's laughing, so he knows. Even though they work for the same company and they should be communicating and working together, that's never the wastewater plant goes to crap, and then, hey, what happened? Oh, no, we don't know about anything. And then you find out 2 weeks later that somebody dumped half a drum of something down the drain. So yeah, sanitizers are a big issue. The other is filamentous bacteria. So there's lots of different things that can cause filamentous bacteria within a biological system. Low DO, presence of fats, oils, and grease, that F-to-M ratio being too high or too low, just a lot of different things. But you can kind of tell from the picture, they look like spaghetti. And what they do is they just prevent, sometimes there's certain types that cause foam, but almost all of them, because they have all the surface area, you can tell it just makes it really hard for the sludge to settle. So if you're relying on a gravity clarifier to separate your liquid and solids, these guys are going to give you lots and lots of trouble. That's why good facilities are monitoring all these different things, all those different parameters that I reviewed. They're reading those on a daily basis, understanding where they're at to try and prevent those things from happening. And when are you doing the bioaugmentation piece? So then there are products that will help you recover from an outbreak of filamentous bacteria in your system. Questions on aerobic? One of the things I should mention, and we should probably add it to this slide, is you hear about membranes a lot more in wastewater applications these days. And I'm going to buzz back really fast just to give you some perspective. So we talked about where these costs come in. And so a lot of times the cost is in the solids liquid separation. So if you think of this as a gravity clarifier, you have to feed a little bit of the flocculant to help settle that. This is a real sensitive part of the process, because this is what, if you don't have tertiary filtration, then you're going straight from your solids liquid separation into your effluent. So if you have filamentous bacteria and you can't settle, then you're at a risk of violating your permit, because you're going to have solids carry over and go out. And so they're really susceptible to upset. So what a membrane system will do, we don't like membranes because they kind of X out this chemical here, which is kind of how we make our living. But what membrane systems are gaining more popularity is, it's a physical barrier between this process and your effluent. And so it's kind of like a filter, but you're kind of like an RO, if you're familiar with those sorts of things. Lots of the time they're ultra filters instead of actually reverse osmosis membranes. But it's a physical barrier. So you can have things go into crap here, but since you have that physical barrier, you can still kind of run without having to be a risk of violating your permit. The other thing that's nice about them is a lot less footprint than a conventional gravity clarifier will require. So if you're kind of landlocked, you don't have a lot of space to add a whole new gravity clarifier, something like that, then they can be a good benefit. So that's kind of one of the new things that's out there. So anaerobic, Chris mentioned anaerobic a little bit earlier. So anaerobic without air. So you can tell the difference on that first picture is you had an open top tank, you saw the brown mixed liquor, it had the surface aerator that was mixing it and spraying it around. Anaerobic, this is, Chris, I think, showed a picture of a tank with a dome top on it. This is the picture of a facility that we have where they just have a flexible membrane cover. This is what they call a downdraft mixer, just where it's kind of like a boat propeller, just forces things down and just kind of keeps it circulating this way. So it's covered, and you have to maintain temperature and mixing, and then it'll generate methane, have gas recovery piping around the perimeter that will then take the methane out, and then you have to decide what you're going to do with the methane. Again, it's an anaerobic biological process which uses microorganisms to biodegrade or to organic pollutants. So again, a lot of the same ideas as activated sludge as an aerobic process, just different bacteria, different equipment required. Similar here, in general, similar. Instead of generating CO2, you're generating methane, and you're still getting new microorganisms. So I always say, I always think anaerobic digesters, probably because I don't understand them quite as much, is a lot more complex process. There's 4 stages and lots of different bacteria involved. And so if you're interested in this, I can refer you to somebody who can talk you through it. But just for me and communicating to you at a basic level, it's a complicated process to run and maintain. Once you get it running, very good process. It will treat a lot of waste and give you a usable byproduct. So this is the biggest thing. Well, not the biggest thing, but I think generating biogas. You can now do something with it. You can run a generator. You can run a boiler. You can just burn it. It's kind of a waste, but there's a benefit to doing it. You can put a lot more organic loading into a digester than you can into an activated sludge aerobic system. I mean, we'll take the high strength waste right out of a cream cheese factory or a mozzarella plant. Those first flushes in your CIP process that have a lot of organics, and they'll send them right down to this type of a facility. You'll generate less sludge. For every pound of COD that you're treating through a digester, you'll generate less sludge than you would through aerobic. Again, for me, a little bit more complicated process to control. People that know it and do it are pretty comfortable with it. You cannot, I should say, I don't know that you can't, but it doesn't remove as much organic matter. It doesn't treat down to the levels of COD or BOD that an activated sludge system will. So it's in that more complicated system that I showed you where they have both aerobic and anaerobic. The anaerobic treatment, the clean water that comes out of that then gets fed into the aerobic to be treated to a level where it can be discharged to the surface water. It's not as good at moving nitrogen, phosphorus, things like that. And then the sludge doesn't settle, so you really can't use a gravity clarifier. So you'll have to use a DAF or some other type of a membrane system to separate the liquid from the solids. Because if you actually take the mixed liquor from a digester, you'll see the gas bubbles just kind of almost fizzing a little bit, and it carries a lot of those solids up to the top, and you can't treat it. Temperature is critical in an anaerobic system, so 85 to 95 plus or minus to maintain good microbiological population. I know that there's some systems that run higher than that, and they have their places, but in the basics of what we're talking about, that's the general range. pH is important, just as it is in an activated sludge system. Volatile fatty acids, it's just part of what's generated in the anaerobic digestion process. If you get too much of them build up, then you can create a sour digester because your pH will drop. And actually what they look at is kind of this ratio between volatile fatty acids and alkalinity as one of their key operational parameters to start to identify problems. If this number changes a lot, then they know that they're running into some issues. Mixed liquor suspended solids, same thing as it is in aerobic, is just you're running much higher. This number on the aerobic system was what, 3,000 to 6,000. Here we're running 20,000 to 30,000 milligrams per liter. So a lot thicker sludge than you have in an aerobic system. Again, too much or too little can cause issues, The other thing that you can do to monitor how well your system is performing is the quality of the gas that you're getting. So there'll be a range of methane and carbon dioxide and nitrogen, and they have sensors that can read those. And if you start to see changes in your gas quality, it'll be an indication that you're having some process upsets. Hydrogen sulfide is a kind of a nasty side effect. In an anaerobic digester, you'll catch it in the air and things like that, and it can be kind of a problem too. So you'll see in a digester facility, you'll see lots of gas monitors around just checking for too much hydrogen sulfide. Just a picture of what the inside of a digester might look like. Again, you're looking for complete mix, but you also have different zones where different things are happening. This is a side of anaerobic that's critical from a safety standpoint, and that's gas management and gas safety. So it's a flammable gas that you're generating. So you need things like condensate traps, you need flame arresters, flame checks, just all sorts of safety devices. So in case something does spark and there is a fire, that it doesn't cause a problem. I think there was a digester out in Madison a couple of years ago that blew the covers off their digesters. I don't remember exactly what the situation was, if they didn't have all the right equipment, but obviously somebody designed or did something wrong. But it's a safety factor.
In a dairy farm?
Not the one that I'm thinking about. This was actually a manure, I think like a commercial manure digester. So I'm sorry, when you say dairy, I always think milk plant, but I think it was manure digester from, yeah. I think it was in Dane. Oh my God.
I think some.
Yeah. I won't spend a ton of time on this because Chris went into this in quite a bit of detail, but solid liquid separation, this is the important part to, once you've done all the hard work of treating your water, you want to make sure that you separate all the solids from the clean water so that you can discharge it. So if you go through all that work to treat it and then you have solids flowing over your weir, you're going to violate your permit, and you did all that hard work for nothing. So gravity clarifiers, this is the same place in Southern Indiana that I ran. I actually fell in that clarifier right there.
Oh,
It's really warm water. The mechanism, so there's a rake, the people online can't see this, sorry, but there's a rake that goes around and just takes the scum off the top. And it was a situation where I was working a week, home a week, working a week, and I was on my Friday to go home. And all of a sudden the rake on one end was up out of the water and the other end it was under the water. So something had gone wrong. So I got in a boat to kind of check this out and see what it was, see what I could see. And as I was getting out of the boat, hanging onto this, I slipped. So I was wet on my way home. So anyways, so a healthy aerobic system, the mixed liquor will settle by gravity. This is basically a wide spot in the line that lets everything slow down, solids sink to the bottom, and then the clean water overflows your weir and goes out. If you have an upset condition, if your clarifier isn't sized properly, sometimes you'll use a little flocculant or a coagulant to help just speed up how fast those solids settle. Then you have to take the solids off the bottom, return them into the process. They're typically around 1% solids towards the bottom of the clarifier. Again, you can tell, big footprint. So this is 1 million gallons, 1.2 million gallons a day. They take up lots of space. This place had a ton of space. Some places do not. Dissolved air flotation, Chris talked about that, so we won't go into it too much. Biggest benefit is smaller footprint. This is a round, this one's funny actually, it's a round DAF in a square tank, kind of unique. This is a rectangular DAF. But again, using air bubbles to float those, typically using in conjunction with coagulants or flocculants. Much smaller footprint, higher cost of treatment because you have the recirculation system on the DAF. That's typically a higher pressure pump, compressed air. Compressed air is not cheap to generate, and then some type of coagulant or flocculant, so a chemical cost that goes with it. DAF is great technology, but it's not the cheapest technology. Here's the membrane systems we talked about. They're bad for us, but good for end users where they're appropriately applied. Not affected by upset, so you can have a biological system that's upset, and sludge isn't settling, but you don't care because you have a physical barrier between your solids and your liquid. So you kind of keep rolling until you get things under control. You don't need coagulants or flocculants. You will need some sort of cleaning chemistry, because with any membrane system, membranes have the tendency to become fouled. So you need some acid caustic, sometimes a sanitizer, just to clean those off and keep them performing well. So Chris talked about this a little bit too. This is actually one of the multi-disc filters. So we provide chemistries for this system here. But again, just the idea here is, if you're looking at this gravity clarifier and you've got 1% solids coming off the bottom of this clarifier, what do you do with that? If you do not have, this place had acres of retention ponds behind it. So they just took their 1% and they dumped it in their pond and no problem. Places that can't handle that volume, if it's only 1% and you have to haul it, you're going to be doing a lot of hauling. So in those types of instances, having the ability to thicken your biosolids is going to, there's a cost of operating this, but you're saving on the side of how much you're having to haul. So that's the purpose of these. So I won't go into too much because Chris talked about it. Typically, the idea between thickened and dewatering is, thickened is typically less than 15% solids, dewatered is greater than 15%. Less than 15%, it'll kind of, under 15, it'll be kind of like a cake, but still kind of, what's the consistency? I'm just trying to think of like really soft Play-Doh, if you will. I mean, it's kind of solid, but you can squeeze lots of water out of it yet. 15% and up, and it's pretty dry. If you squeeze it in your hand, it'll form to your hand and retain its shape. You can stack it pretty high. So just, again, he went through different types of sludge presses, so we don't have to talk too much about those. I don't know if he talked about, this was one that we did treat. It was a rotary press. It was really, really difficult to treat. He talked about centrifuges, so I'll jump through those. So comparison, so we talked about aerobic and anaerobic systems. Treatment quality, typically aerobic, you can go to surface water. You have nitrogen, phosphorus, nutrient removal, so you can discharge to a surface water. Anaerobic, again, typically you're going to have to treat it in addition to, or if you have a pre-treatment scenario where you can send it to the municipal wastewater treatment plant, you can use anaerobic and then just send the effluent from that down to the city plant. You can see here, so this kilograms of COD per cubic meter per day, that's an expression of how much loading they can handle. You can see these numbers are very different, 0.5 to 1.5 kilograms for an aerobic system, 3 to 20 for a anaerobic system. So that's just an indication you can really load up an anaerobic system with a lot of waste, organic waste. Then also a comparison of the yield rates, just kind of in reverse, much higher yield rates on your aerobic systems compared to your anaerobic systems. They'll kind of balance out though, because if you send a lot more waste, you have a lower yield rate. So in the end, you might end up with the same amount of solids, right? So it all depends on what the loading is and what your actual yield rate is. Lots of energy costs for aerobic systems versus an anaerobic system, which can kind of create its own energy. If you have enough waste going through, it can actually power an entire plant. Chemical, low if you're using a gravity clarifier. Here you're going to have higher chemical usage, A, because it doesn't settle, and B, because your mixed liquor suspended solids are a lot higher. And then sludge disposal, that's all just depends on what sort of assets you have for dewatering and hauling and where you're going with it.